so recording. Right, so I'm starting the recording here. And then sharing the screen here. So we are reviewing the ECNG 2011 exam. Okay, so I trust that you all had some opportunity to look at it. Okay, this is one of the, I mean, the exam is quite a while back, but the topic content is relatively close to what we are doing. There are some things that, as you look at it, you'll realize that we didn't cover, and it's not going to be part of our, it's not part of our syllabus for this current semester. And when I say summer semester, I also mean the semester one when you took the course for the first time. Okay. So what I'm telling you to ignore here is also valid for whatever exam you have coming up. All right, so let's get started. And as usual, if you have any questions at any time, just interrupt me and feel free to let me know, and we'll try to clarify it. All right.
So, is in the 2010 paper you said to do first?
The 2010. Oh.
Yeah, I saw that on the homework announcement.
Okay. And I prepared the 2011. All right, well, look, let's do it a little randomly then. We look at the 2011 paper because I have some slides prepared here, and it's fairly similar. So it will be a kind of cool start, and maybe people could look at it, try to pull it up. You have access to the 2010 paper?
Yeah.
The 2011 paper, sorry, my mistake, 2011. You have?
Yeah.
Right, okay. So pull it up, everyone, and we will use that. Unfortunately, my mistake, I should have said it was only the 2011 paper that I was trying to organize for you. But the same sort of topics will work. So we could, we wouldn't suffer. It will be a little bit, well, maybe in your case, it might be a little bit different because you're seeing the things, and this will be a little more exam-like in that you're seeing the topic and you're kind of being forced to remember initially what it is. Okay, that'll work fine. That's not an issue. And next time we'll do the 2010. Right. So if all of you all are you able to pull up the 2011 paper? Right. In any case, I'll have the questions up there. So if you don't have it, not too much of an issue anyway. Right. So look at it here. All right. So and what I've done here is that for each of the questions where we that are part of the current syllabus, what I've done is that I've put a little text box there to tell you which are the topics, or where in the lecture sequence you will find the slides, and also you can go on and hunt up the video as well to review the material if required. Okay. All right. So let's see what happens here. The first one. This is something that comes up all the time. It was in your last exam. It's here now. So the Barkhausen criterion for oscillation in a feedback system. So the bigger picture here is what, first off, why do we need this sort of behavior for oscillation to occur? We answered it in when we were reviewing the last exam. But again, if you remember, right, and this is something that we've done elsewhere as well, if you have a system, and I'll just use the jargon that we're using for electronics. So you have some piece of electronics, and then from the output, we have a feedback block. Okay, and then we have summing junction here. So we have an input, right? We have an output, and we have some feedback, and we making sure that the feedback is positive. We know from our block diagram and from systems theory, that the transfer function here, xo over xi, is equal to what? X over xi is equal to what?
One over one minus AB.
Is it 1 or is it A over 1 minus AB?
A over 1 minus AB.
Good, right? A beta, right? If you like, for correctness, this is a, at this point in time, this is what we have, right? So A, remember, this is your normal from your signals and systems theory. When we did this would have been our G, and this would have been our H. So it's G over 1 plus or minus GH, right? It depends on whether the feedback is positive or negative, right? If it is positive feedback, we have a negative sign here. If it is negative feedback, we have a positive sign. Now, the thing about it is that if we watch this factor here, if the magnitude of A beta is equal to 1, then this denominator goes to 0. In other words, 1 over 0, so you'll have A over 0. So what you're getting at here is that XO will be approaching infinity times X in, right? Now that is a marvelous kind of arrangement, in that what this really is saying is that if you have something that is as big again as infinity, that the littlest input that you have, X in, remember X in is the input here, the littlest input that you have is going to be multiplied by a huge number, and you're getting an output. So in theory, what this means is that for 0 input or close to 0 input, we could keep getting an output. In other words, if we make A beta equal to 1, this system will keep giving an output even though we don't have any input. All right? That is part 1 of the criterion here. So if we want this thing to give us an output without any input, then A beta, the magnitude of A beta has to be 1. The other part of it is this here. This depends on having positive feedback. That's how we got a negative sign here. Positive feedback means that whatever signal I have here, the signal, when it adds back to the input, has to be in phase with the input. So the input, we have some input coming in. If the feedback system, the feedback signal, sorry, is in phase with that, it's going to add. If it is not in phase with it, then it is going to subtract from X in, and the system will die out. So in this case, in order to get the positive feedback, the feedback has to be in phase. In other words, as you pass through this whole thing, the phase angle of A beta, I'll write it across here, the phase angle of A beta must be equal to 0 degrees or 0 radians, or multiples of 2 pi, right? Because multiples of 2 pi repeat. For sinusoidal signals, they repeat every 2 pi, so it doesn't matter. So you either have 0 phase, or a repeater, or a multiple of 2 pi phase difference. So you can, the circuit here, remember this is all, and always remember this, these are circuits here, circuits and networks. Right, so components in here. So an op-amp here could have an op-amp here, and then you also have a network, And usually the network is R's and C's, okay? So they are real components, and you know that when signals pass through resistors and capacitors, they get shifted, they get delayed and so on, which is where the phase shift comes in. So if we have some way of designing this in such a way that the phase shift is 0 or a multiple of 2 pi, then we are able to satisfy this criteria here. So those are the two things that we need. If for this thing to work, for an oscillator to work, one, the gain, what do you call it? The loop gain, which is A beta, has to be 1, and the phase of that loop gain must be 0. Okay? Oops, this should have been number 2. Yeah? 1 second. Hi, apologies for that. We have the faculty board of examiners meeting this morning, so I have to just answer something there. I'll try to edit this blank spot out of the video before I upload it. Yeah, so there are two things that have to happen for this thing to work, and together those constitute the Barkhausen criterion. All right, but the principles behind it are, the reason behind it is what we have explained here before. Notice that the question, that particular part, I mean, all that time that we just spent was to get the part here for just 2 marks, okay? So for the 2 marks, you would have stated the bit, the items numbers 1 and 2 here, that the Barkhausen criterion. First off, actually, what you should do is that say that the transfer function for the oscillator looks like this, all right? That the Barkhausen criterion says that for a transfer function like this, 1, if A beta is 1, and 2, if the phase of A beta is 0, that you're going to get oscillation in a feedback system. All right? Left to me, I mean, there's a very old past paper here, but left to me, I would have given a little more marks here. I would have probably given 5 marks here, because I would have liked at least for the answer to have a little drawing, this expression here, and the two requirements for the Barkhausen. Okay. Okay. And question part B was that given a circuit here, to determine the frequency and amplifier gain for oscillation to occur, and show the full details of the analysis. And again, all of this is taking oscillators 1 explains the Barkhausen criteria. Oscillators 2 is where the Weinberg oscillator and the other phase shift oscillators are discussed. And remember, the idea behind all of them is to create a network where, as the signal is fed back. Now, if you look at this, thing, you have an input here. So this here could be an input here. This here, the output. So if you, by carefully selecting the values of R and C here, you satisfy the Barkhausen criterion. And well, the amplifier, of course, is just to sustain the gain. And as we said, there are losses in the components, so that the gain, you go back here, this thing where the gain is exactly 1 is something that is ideal, but really and truly, we normally make it slightly bigger than 1 to compensate for losses, because resistances, there are electronic and current losses in the system because of the resistances and impedances in the circuit as well. Yeah? And this one, the analysis of this, as we said before, the amplifier here you could almost ignore, right? That the amplifier facilitates the oscillation, so that the actual phase shift network, if you want to consider, this is the A here, and the R's and C create the beta part for you. And how you evaluate that is, as somebody asked before, how much circuit theory you have to know. you have to know at least how to evaluate a simple. So this is a simple, is a series. You have a Z1 and you have a Z2. So you have two impedances in series, and the output, you have the output across the two of them, and the input is across here, right? Or in fact, the other way around. You could it really doesn't matter. What you need is to calculate this point in terms of here. So you could actually, some people have said that this is the output of the Weinberg network, and this is the input to the whole phase shift network. The labeling is kind of unimportant. The important part is that once you do the division, that the whatever is here, right, is, just to use my original thing, if I had it at XO, right, over Z1 plus Z2, right, and you're multiplying it by Z2, right, and that is the network there. And you look at here, Z1, of course, is R plus 1 over SC. Yeah. And Z2 is R in parallel with 1 over SC. Okay. And once that works, then the rest of the oscillator should behave itself properly.
So what kind of amplifier this will fall under?
What is that?
What type of amplifier will this fall under?
This well, as you have it here, this is a pure operational amplifier. Most of the circuits, if not all of the circuits that we considered in our course, were centered around operational amplifiers, not discrete transistors or anything. So for a number of reasons, the op amp is the easiest thing to design with. And it gives you as close to a perfect amplifier behavior as you can like, so that once you see a circuit like this anywhere, this is an operational amplifier here, okay? Yeah. And in fact, for most of your designs going forward, if you have any, not only here, but let's say in your final year project or something that you want to experiment with, right? Or you have something that you want to interface to a microcontroller or the like, 99 times out of 100, you would use an operational amplifier type of device. If it is very what is called precise work that you're doing, then you can use the other one that we spoke about during the course of the of our thing, which was an instrumentation amplifier. But they are all operational amplifier based, right? So you don't have to worry about a discrete design at this point. Yeah. Fair enough. That answers the question, or was there something else?
Our next thing, so will it be like an inverted amplifier or?
Right. So what configuration do I have here?
Well, the positive, the Z2 connected to the positive of the amplifier, and the negative to that will be grounded.
From the time you see us using this input for the op amp, it means that we're using the op amp in the non-inverting mode. Right? Remember that you want, if you go back to our discussions here, you remember on all what you want is positive feedback. So in other words, whatever we come back with inside of here has to be added back positively. We don't want any inversion. The only phase changes that we need to have are inside of the feedback block, and we have to make sure that that is 0. All right. If I were to run this somehow, if this had been interchanged and I had a minus here and a plus, then what is going to happen is that whatever is the output here is going to be minus, right? It's going to be 180 degrees out of phase with whatever went in inside of here. In other words, it's going to be a minus. So we're not going to have the positive feedback inside of there, right? If that is the case, and if you remember in the oscillators discussion, right, when we did, between, I think it's in here when we were discussing phase shift oscillators, that was the approach that was taken, that you had the amplifier, the phase shift networks. So you went through a series of phase shift networks, and the phase shift network gave you a total phase shift of 180 degrees. In other words, if I had a V in here, what I had coming out was a minus V in at this point in time. And then we sent it to an amplifier which had a gain, which had a negative gain, a gain of -1, so that when you got out here, you had plus V in coming back out. So in other words, if the amplifier gave you the other 180 degrees, this situation we would have used an inverting amplifier. Yeah. So you have to watch the context of what you're talking about. For the Weinberg oscillator, the network here is giving you 0 phase shift, so that the amplifier to take the signal and send it back out without to satisfy the Barkhausen criteria, the amplifier has to give you a gain of +1, right? Approximately. In the case of some of the other phase shift oscillators, which are discussed in that oscillators 2 lecture, and you could check it over. Each of these are RC networks here, and the 3 of them together give you a phase shift. At least the one that we discussed in class gives you a phase shift of 180 degrees. In other words, there's an inversion here. So that to bring it back to reality, the amplifier has to have a gain. If the gain here is 1, then the amplifier has to have a gain of -1. I think when we discuss the circuit and you do the analysis, sometimes you get the gain for these. The phase shift is 180, and the gain might be some value A. So you have to have a gain of -A on the amplifier. Remember, there was a question, I believe, in the last exam that asked you what was the gain of the amplifier, right? I think the gain was 8 or something, -8 or something like that. Remember that? We discussed it last week when we were looking at the last exam. Make sense?
Yes, sir.
All right. So if you want, in summary for that particular point, if the phase shift network is not giving you any inversion, so the signal coming out of the phase shift network is in phase with whatever goes in, then you're using a non-inverting amplifier. You'll have to compensate for the gain and that kind of thing. That's fine. If the phase shift network is giving you some sort of phase shift, then the amplifier, especially if at the end of the phase shift is a 180 degree phase shift, then the amplifier has to compensate by giving the additional 180. And we understand that a 180 degree phase shift is an inversion, right? So the amplifier will have to have a negative gain, in which case you have to use the inverting, the inputs you will see will be going to the inverting input of the amplifier, right? Okay. And then, right. So after having calculated, once you do all of this, you get that the final transfer function of the Weinberg what do you call it, network, and the amplifier is something that looks like, we have the answer here, so I'll just write it down, right? You get that beta is equal to SRC over R plus 1 over, sorry, I missed it. Copying the wrong thing here. Right, over 1 plus 3 SRC plus S squared C squared R squared. Right? So that to get the frequency response, so of course, if beta is that, then A beta, which will be A by this, has to be equal to 1 for the Barkhausen criterion to work. And then if you substitute S equal J omega, you get something inside of here. And that's going to allow you to determine the value of omega to make A beta equal to 1. And if you do that, you get that both the gain for this circuit is 3, and that omega is 1 over omega is equal to 1 over C, or if you want, F naught is 1 over 2 pi C. So the thing about this particular type of oscillator, first off, if you look at it, and this is something that you're going to see in all the other networks as well too, these things have to match. So this capacitor and this capacitor have to be equal. This resistor and this resistor have to be equal or as close as possible. And we spoke about that too when we were talking about using real components. So if you're going off and you're buying components, you remember resistors typically, if you buy it off the shelf, resistors have like a 5% tolerance, right? Capacitors have a 5 to 10, right? So if you design something inside of here, usually for a network like this, right? Once you have that here, you want to oscillate at 55 kilohertz. That's what the question is asking for. You pick a value of the capacitor. So you pick a capacitor here, let's say 1 microfarad. And then you substitute inside of here to get what R is, whatever that turns out to be. If you're going to actually make it now, remember when you go and buy your capacitors, that this one you get, you go to stores or you go somewhere and you get 2 1 microfarad capacitors. Usually they will be, 5%, 10% kind of thing, right? 5%, even 10%. Okay, same thing with the resistor. So whatever resistor value we calculate for here, whatever that answer happens to be. When you calculate it, you remember that it is a 5% tolerance that you're dealing with. So the best thing to do is that you measure it, because you don't want one R plus 5% and the other one happen to be R minus 5%. Then when you put it on and you put this on your breadboard and so on, and you try to make it work, it's not going to, right? And then you'll wonder why. You go back and you try to figure it out, but wait a minute, I did all the theory, I did everything correctly, but the thing is not working. And 9 times out of 10 will have to be because the resistors or the capacitors not matching closely enough. Okay. All right. So that's sort of practical slide. Yeah.
When you calculate any resistor and capacitor, one you'll have to assume is like for something, I think it's a capacitor at 1 milliamp or no, 1 microfarad.
Mm-hmm.
What was the reason for assuming it is 1 microfarad?
You pick up, okay, so you have to start somewhere along the place because the oscillator, you need both an R and a C. So you have to make a choice. So you try an educated guess. Capacitors, 1 microfarad, 10 microfarad. Remember, I think earlier on I'd given you all a little list that some of these components only occur in certain fixed values. So you start off with a 1 microfarad and you see what R gives you here. And you use that. the alternative would have been to start off with a particular value of R and then see what capacitor you value you get. You have more, what shall I say, more options in getting resistors and getting capacitors. So if you had to pick one to start with, is usually better to start with the capacitor. No, the capacitors, of course, you get 1, you get 0.1, you get 5, you get, and there's a series. I'd given you, I think I'd given you some information or a link very early on about the typical sort of values that you get these components in. But you have to make a choice. And in exam, I'm not too concerned about whether it's a full practical choice or not, but pick one and calculate the other for me, right? So if your approach was to say, okay, let me pick R as 100K and calculate the capacitor to something, that is fine. If you pick C as 1, and you get R as some value, that's fine. If you go and you pick C, and let's say for some strange reason, it is a high frequency thing, but let's say you pick C as a very big capacitor, like 1,000 microfarad, you're going to get a very, very small resistor. And if you tell me now that based on that R is, let's say, 0.05 ohm, and give me that as your answer, I'm going to have a little problem with that, because that you need to think in terms of a real world context. Okay. All right.
But just the reason for choosing, like, not just those are the standard values, but is there a reason for choosing the capacitor at that value?
No. I could have as well say 0.5 micro or 0.1. If you play around with electronics, you know the sort of values of the capacitors that they could actually get. So I'll pick one of those. If the circuit is asking for 55 kilohertz, I think the question, right? So 55 kilohertz means that the capacitor is going to be relatively small. Look at look at it here. So 55 kilohertz here means that either the resistor or the capacitor is going to be small. All right. So you have to pick one of them. So you pick a smallish capacitor and then see what value resistor you come up with. If you pick a big capacitor, to make this work, the resistor is going to be incredibly small, which is what the little joke I was making, of course, on this side. All right, but you have to pick one or the other. So looking at this thing, and from experience, if 55 kilohertz, that's relatively high, it means that these two things below here have to be kind of small. So the product of R and C have to be small so that F0 is kind of on the high side. So you pick a small capacitor, just a rule of thumb. A small capacitor, 1.1, you could even get away with 0.1 microfarad, that's good. Right, so 0.1, 1, 0.5, those kind of values, right? 10 might be a little bit too high. Okay. But I wouldn't penalize too much if you were to say, okay, use C as 10 microfarads and you get a value of let's say 100 ohms. It won't be 100 ohms, right? But something kind of small and so on. From the time you start to, if you pick a value and you start to get the resistances less than 100 ohms, then choose a smaller capacitor, okay?
Mm-hmm. So just choose a capacitor and build the circuit for the frequency around it. Yeah.
In all of these circuits, the sort of frequency selective component, if you like, is the capacitor. So you pick the capacitor first and get the resistors, because, as I said, it's easy to get, if you get an oddball, so you pick, let's say, the capacitor is 10 microfarad, and you get something like, in practice, you get R as 540 ohms, just for argument's sake, right? Not that that is the answer for this bit. But 540 ohms is not a value resistor you could get, but it is a value that you can make. Remember, with series and parallel combinations of resistors, you can make nearly any value that you want. Mm-hmm. So it's fairly easy to create an odd value in a practical application. It's a lot easier to create an odd value of resistance than it is to create an odd value of capacitance. Okay.
Yes, sir.
So that is just from the sort of the hands-on fiddling, building circuits. All of this thing is all well and good to discussing in theory. But as I've said before, electronics is something that you're really supposed to be applying somewhere around the place. So you need an oscillator for some reason, and you want to design it. You go ahead, and the practical approach is to select the components that are off the shelf, closest to what you have calculated, and then see what you need to create elsewhere. Yeah?
Yes, sir.
All right, so let me see.
So, one last thing, right? To get that gain equal to 3, right? What you're doing is substituting S equal to J omega into the formula A beta, right?
Correct.
So, you rearrange, you take the denominator and carry it on the next side, all right? And then when you substitute, you throw all in one side and put it equal to 0, and you solve for A.
Correct.
Is that?
You're going to solve for two things at once. You're going to solve for both A and omega. Remember, when you substitute, just look at the bottom here. Let me write it in some different color ink. That's not what color we haven't used as yet. Green. Right. If I substitute here, I'm going to get 1 plus 3j omega r c here, minus omega squared squared c squared, right? So, and then of course you have a j omega on top here. But just for argument's sake, look at the bottom here. For the phase shift part of it to be 0, it means that this bit will have to be 0. Okay? I haven't cross multiplied, but just the behavior of it. For you to get a phase shift where you have a complex number like a 1 over A plus J beta, for the phase shift of something like this to be 0, the complex part has to be 0. In other words, when you do the substitution and you cross multiply and simplify it, everything with a j in it, you will set to 0, and that's how you're getting the omega from that. Okay, and then the other part will tell you now from that, once you get the omega, it's going to tell you what A is going to be. You're going to get A in terms of all of this and in terms of RC, and that's where the 3 comes in. Yeah. So 2 things going to come out of it when you do the substitution. Yeah.
Yeah.
Okay. And then of course, when you get the gain of the circuit is determined by these 2 here. It's a non-inverting amplifier. So what's the gain of an op-amp non-inverting? What's the gain of a non-inverting amplifier? RB is the feedback and RA is the ground resistor. So what's from that as a year 1 here? The gain would have been 1 plus
R. It will be the resistor on top over the underneath resistor.
Right. If this is the feedback and this is the ground resistor, right, from the general circuit. So it's 1 plus 1 over RF, 1 plus RF over RG, right? RF is RB and RG is RA in here. So if you let this has to be 3 for this particular circuit, again, like we did before, you're going to have to pick a value of one of them. So you pick a value of RA or RB, and then you solve for the other one in here. Okay? So it's a number of things. You analyze the circuit from a practical thing. You're given this thing, let's say it was a lab exercise that you had to go, and at the end of the lab exercise, give me an oscillator that was giving me 100 kilohertz. So you're going to have to get, first off, you have to analyze the circuit. You have to get the oscillation frequency. You pick the capacitor value, you calculate the resistor value. So that's giving me that part is going to solve the 100 kilohertz part. But then you need a gain of 3. So you go to the other part now, the op-amp, the non-inverting op-amp. You pick a value for either RB or RA, and then you solve for the other one in order to get the gain of 3. And then you breadboard the thing, you put it together, and then you turn it on and see if you are getting 100 kilohertz or close to 100 kilohertz. If the resistance values and the capacitance values have a tolerance of like 5%, then whatever comes out of this is going to be the frequency plus or minus a 5, at least a 5% sort of value, right? So it's very unlikely that if you design this for, well, the question is asking for 55 kilohertz. If you design it for 55 kilohertz and you actually breadboard it, when you measure it with a scope that you're going to get 55 kilohertz, you're not, right? You'll get somewhere, it might be a little bit above, it might be a little bit below. And the explanation, of course, is the tolerance fit. Right? If you remember when you did your physics labs and your chemistry labs and so on, you always had to comment on why the values are a little bit different from what the calculated value is. So you do a titration or you do some sort of experiment in physics, and you had to comment about the errors, right? And of course, things like significant figures and so on. So all of that contributes to this. And remember that too later on when you all start to do a final year project as well, that when you design a circuit and it works on paper, when you make it in reality and you put real components, the value of the thing is going to be a little bit different. And you explain that it's different because of the component values and so on. And then you use what is the actual frequency in it for whatever calculations you have going forward. Okay, so you don't propagate an error going forward in any design. All right? Make sense? All right. And the last part of the question had to do with stabilizing the output signal amplitude. If you remember, if you remember, I mean, this is a little bit scrappy. Remember that the ideal behavior here will give me a nice, just let me go back here. Let me end the show and start it over. So you can discard this. You'll have this in the recording anyway. Good. Ideally, once you design this thing, you're supposed to get a nice sinusoid coming out. But because of the variation of the components, because of things like the op-amp and the components getting warm because they're carrying current and so on, what you find is that the amplitude here could start to deteriorate. And as you go along, it could die out. Or the other thing, it could start doing this and then it start getting bigger. And then if the if the op-amp is powered, let's say by plus or minus 5 volts, then at some point in time, when the output gets, the highest the output could get is a VSAT, plus or minus VSAT, which let's assume is close to the power supply. So at that point, it's going to get close to here and try to get bigger. So what's going to happen is that the output going to do that, clip, do that, clip. And then eventually, if it keeps getting bigger and bigger, all you're going to get now at your output is going to be looking something like that, right? In other words, the output saturates. So what is normally done in these circuits is that you have to stabilize the output. And we saw that there were 2 ways of stabilizing the output. In fact, there were a number of ways, and that's discussed in the Oscillators 4 lecture. One is to introduce a device called a thermistor as one of the elements in it. So you put a thermistor as part of the feedback resistor. So as it gets warm, the thermistor value drops and the gain of the circuit goes up so that it tries to compensate for this thing. So as the gain gets bigger and the thermistor gets warm, the resistance value drops, so the gain drops, and the value of the sinusoid or the output gets back to within the normal range. And then as the thermistor warms back up again, it will try to compensate for the amplifier output going up and down. The other way that we showed that we could do it was to put on the output 2 back-to-back Zener diodes. Right? So you put the Zener diodes on the output. So if this was VD1 and VD2, as soon as the output here exceeded the value of VD1, right, that particular Zener diode would start to conduct and prevent the amplitude from getting beyond that. And same way, when it went negative, if it got less than minus VD1, then it would start to conduct and bring the amplitude and limit the amplitude to whatever the Zener diode voltages were. So any of those two would suit the answer for this part. It's just 4 marks for it. So briefly, what you want to do is either to look in the circuit and say, well, you can replace the feedback resistor by a thermistor, or you can put the 2 back-to-back Zener diodes at the output to stabilize it. Yeah, and that is all discussed in this particular lecture where we spoke about amplitude stabilization. Right. So questions? Yeah. We all right with that?
Part C is where we will be using the RB and RA.
Yeah, well, you have to change one of them, right? Because RB and RA give you a fixed gain, in this case, a fixed gain of 3, we know that as a circuit works, this gain is going to change. Usually it will go up. So what you want to do is to compensate for that by changing by replacing one, either RA or RB, by a device whose value changes as the temperature goes up. Right? The easier one is the thermistor. There's the other one, the thermistor, the resistor goes down as the temperature goes up. Then there's the sensistor, which the other way, the resistor goes up as the temperature goes up. And the last approach was to use the two back-to-back Zener diodes. And the last part of the lecture showed that, and also showed a screenshot of Weinberg oscillator. This was simulated in multisim, and the screenshot to show you how the Zener diode version worked. Okay, this is the easiest. The Zener diode practically is the easiest one because it's easier to get Zener diodes and thermistor values to what do you call it, to match your particular gain. So if you need, you know, like a 1K thermistor or something, so a 5K thermistor is a little bit harder to go and find that than if I say, okay, they are working between plus and minus 5 volts here. So I'll stabilize the value between, let's say, plus and minus 4 volts for argument's sake. All right, I could go and get a 4 volt, a pair of 4 volt Zener diodes and put them in here and get the stabilization working. Yeah. All right. So that was we almost finished here. It's 8:57, so I have to go to the examiner's meeting shortly. So what we did here was basically to do in the course of this question to do a review of some of the behavior of oscillators. There are other oscillators that we spoke about, and you are going to have to inside of here. You're going to have to look at the phase shift oscillators, right? So we did the Weinberg, right? W-I-E-N, I keep W-I-E-N, Weinberg and phase shift. Those were the two main ones inside of here. We also discussed crystal oscillators as well in our oscillator discussions. And here, but the last part of this had to do with amplitude stabilization. This one had to do with the Barkhausen, right? And why oscillators work. Okay, so all of that basically in one sort of question here. And so next time when we meet on Friday, we will look at power supplies next. All right. And if I had you by in error revise, look over the wrong question paper, but it's not. It's that's all to your benefit, because it just meant that you're ahead of the game a little bit in reviewing the material and so on. Okay, so I'm trying to do within the time that we have you have the solutions, so I don't have to go over the solutions, but clarify explanations that you want clarified. Okay. Somebody has sent me a question and I didn't reply to it as yet. Okay, so I'll get to that, or other people feel free to try to respond to it. It's nice if there's a question on the discussion forum and other people chime in with what they think the answer is, and I could get an idea of if people are kind of on the right track or if there's a misinterpretation going along. Okay, there's no such thing as an error or doing the wrong thing. The most that could happen inside of here is that you will misinterpret something or misunderstand. Okay, so don't be concerned if you put up something and the answer isn't what it is supposed to be. Right? What you have there is a misunderstanding, not a mistake. Okay, and we'll clear up all of that. All right, so that is it for today, folks. Thank you for attending.